We're going to finish talking about what sets can't be done with finite state machines. We did this idea of diagonalization on Sunday, which is this jackhammer of a tool that always can spit out a set kind of outside of its collection. And we banged diagonalization on finite state machines and found out that there was the set of binary strings that represent finite state machines that don't accept themselves, and that set couldn't possibly be in our list of finite state machines. And that idea, the barber who shaves everybody except himself, the finite state machine that accepts everybody except itself, those kind of things is what diagonalization is about, and they always produce kind of the exception, the thing you're looking for. Except for finite state machines, it's better to use more subtle tools, not the huge jackhammer, because there's a lot of other more simple sets that are also not able to be accepted by finite state machines. And the main way we do this with finite state machines is with a tool called the pumping lemma, which we've talked about informally up till now, but never formally. And we're going to do it very carefully today with some very specific, detailed examples. Finish with that. Depending on where we're up to, I have two more topics that I may do today, and here's what they are. One is I want to finish that triangle of equivalence for regular expressions, deterministic finite machines, and non-deterministic finite state machines, and add in one more, make it a foursome, called a right linear grammar, or a left linear grammar, one of those, and talk about grammars. That's one thing. The other thing is I want to show you how to minimize a finite state machine. My gut instinct is that I want to leave the minimizing the finite state machine to a separate day, because I want you all clear and fresh, and it's kind of a topic that is a little open-ended in the fact that the algorithm we actually use, the idea is not too hard, but then how you actually implement it, there's a lot of different ways. And I'm leaving one of those ways for my triple extra credit problem set. Triple extra credit. It's like triple chocolate brownies.
Was that the one that was someone's famous paper? Or?
Yeah, that's right. Actually, it's not like, oh, gee, I can have a homework problem, you know, that was like a well-known paper. But the truth is, what happens with well-known papers is that they slowly integrate themselves into the graduate textbooks and then into the undergraduate textbooks as exercises. Typically, by somebody telling you something can be done, it makes it much easier. And then secondly, by somebody giving you a hint about how it can be done based on the stuff in the chapter, it sometimes makes it really not so difficult. Nevertheless, this particular problem is a famous paper, which is how to minimize a finite state machine in order n log n time. The really simple way to do it is n cubed. If you think about it a little more, you get it down to n squared. And this paper got it down to n log n. I don't think it can beat that. So in every finite state automaton book that's fairly large nowadays, you can find this question as a double star or an extra credit problem at the end of the chapter. You know, here's a hint about how to do the data structures. Make the algorithm work in n log n. And then they'll give a reference to the initial paper, which I think is by Hopcroft and Ullman, who wrote one of the textbooks on theory of computation and did a lot of work in it over the years. So I threw it on because it is something interesting to think about. And for those of you who like algorithms and programming, it's a fun programming project too. But we won't get to that probably today. We'll probably do that tomorrow. I'm going to spend today talking about pumping lemma and about these ideas of a linear grammar, or what a grammar is. Okay. So, pumping lemma. Okay. As I said before, the pumping lemma is used to show or exhibit or prove that a set is not acceptable by any finite state machine, that it exists outside the horizon of finite state machines. And the way it works is, it turns out that if you have a set that is accepted by a finite state machine, that it has a certain property. It can be pumped up somehow. We'll be very specific about what that means in a minute. Therefore, if you can show that a set does not have that property, that pumping property, then it couldn't possibly have come from a finite state machine. So this lemma is written down in the forward way, usually. If something is a regular set, then it needs this then it needs to have this property, this pumping property. But we use it backwards. We use it to show that, give me a set, I'll show you it doesn't have this pumping property, and I will therefore conclude that it can't be a regular set. So the pumping lemma is written as regular set implies pumping property, but we use it in the contrapositive way. I don't know if that's the right word, but we use it the backwards way. Not pumping property implies not regular set. Remember that A implies B is the same as not B implies not A? They're identical, and it's logically equivalent. We did that many months ago. If not, just think about it. They really are equivalent, and they're the same logically. OK, so the first thing is, what is this pumping property? And then once we write it down rigorously and carefully, how do we show that some set doesn't have it? And it's very much like this dialogue we went through in the last lecture and the lecture before. But today we're going to do it very, very specifically, now that you've got the background. So here's what we do. Somebody gives you a regular set. That means there must be some finite state machine that accepts it. Let's assume you calculate the finite state machine, and you have it in front of you. Then here's what the pumping lemma says. Let me write it out in real detail. It's going to take a whole board just to write it. If L is a regular set, then all right, I'm going to say it once intuitively, and then we'll write it down in detail. If L is a regular set, then if you have a string in L that's supposed to be accepted by this machine that's long enough meaning longer than the number of states in the machine that accepts it, so that it has to loop. If you have a string that's supposed to be accepted, and it's long enough so that it has to loop in its computation, then there exists that loop, and that if you pump up symbols in that loop, the resulting pumped up strings also have to get accepted. That's basically what it says. But writing it down rigorously is going to be ugly. There's no nice way to write this. If L is a regular set, then for every, this is the abbreviation for every Z in L, Z is a string, so for every string in L where the number of symbols in Z, that's the sign for the number of symbols in Z. The number of symbols in Z is greater than or equal to the number of states in the machine for L. Okay, so that's the first step. For every string in L where it's long enough, where it's bigger than the number of states in the machine for L, what then? How do you continue? For every one of those strings, there is a way to split that string up into three parts. The first part is the part that goes up to the first loop. The second part is the actual loop itself. And the third part is the rest of it. Keep in mind that the third part may have loops itself. Okay, the second part is only the very first place that you find a loop. So there's going to be a way to split Z up into three parts. The first part is up until the first loop. The second part is the loop itself. And the third part is the rest of the string. So we write, there exists. That's there exists.
Is there a symbol for what you just said?
Yeah, it's called. There exists VWX, three parts, such that Z equals VWX. The string we were given at the beginning is equal to the concatenation of these three, put one against the other. And there's some conditions on VWX that help us and give us some power here. The loop has to come within the first, let's give this a name. Instead of saying number of states in the machine for L, I'm going to write a line up here. There exists an n equal to the number of states in the machine for L. That'll save me writing this over and over again. I can just write n. If nobody minds, I'll do that. Okay, so if L is a regular set, there exists an n equal to the number of states in the machine for L. And for all the strings in L where the number of symbols is bigger than n, then there's three parts to it. You can write it in three parts. Such that what? What about these three parts? The loop has to come in the first n symbols. Okay, the VW. So by the time the VW is over, you can't go more than n symbols. So we write that like this, such that the VW part is less than or equal to n. All right, everyone understand that? So by the time you're finished with the loop, you can't be past n symbols. The loop has to come within the first n symbols. What else do you know? There's one other piece of condition you know about VWX.
X is also something that is.
No, x could be
Oh, wait, I mean,
x could be very long.
but
Because z could be very large. Z could be 100 times n.
we're talking, and there could be more loops in X.
And there could be lots of loops in x, right? We're just talking about that w is the very first loop. But there is something that you do know. Maybe it's just obvious, so you wouldn't think of saying it. But the loop has to really be a loop. It's not just an empty, vacuous loop. I mean, there's got to be at least one thing on this loop. It could be 4 or 5 things. It could be 20 things. But it's got to be at least one. So we say that the w part has got to be at least 1. All right, so there exists VWX such that all these things are true. And for every I bigger than or equal to 0, VW to the IX is also in L. I can pump up the middle part as many times as I want, and that resulting string will end up in the same final state as the VWX did, because all I'm doing is saying follow those symbols again on the loop and then continue the way you did before on the X. So as many W's as you want will still get me to a final state, which means that VW to the IX is also in L. Remember, this exponentiation means repeated concatenation. Just means doing it over and over again. That's what the pumping lemma looks like. It's long. And there are, if you want to think of it, 4 quantifiers. There exists for all, there exists for all. Right? That's the kind of theorem that it would be nice if math had better symbols for, and there was a nicer way to write it. But there just isn't, so we write it this way. We write it all out. I think this is much harder to understand if you just saw it on the board than the dialogue we had the other day, which is much more intuitive and makes a lot more sense. All right, let me stop for a second. Are there questions about this? Yeah, Donna.
Are V and X just the stuff on the other side of the loop?
Yes.
Okay.
V is the stuff on the left side of the loop. X is the stuff on the right side of the loop. There is no loop in V. There might be lots of loops in X. I should say, there's different versions of the pumping lemma. I'm giving you a very nice version which kind of insists on the loop happening early because we can insist on that. And we can ask the person, give us the first loop you find. And that makes our job easier when we use this later, you'll see. There are versions in books you'll find that don't insist on this particular condition. And because they don't insist on it, it makes the proofs later on harder. It's kind of a weaker pumping lemma in those books. So this is a strong version, and it's nice. What about I being 0? Is that okay? That means I don't even go through the loop at all. I just avoid the loop. I just take out those symbols. Would it end up in a final state or wouldn't it? I go to here. Instead of going on the loop on my normal middle part, I take out that middle part and I continue on. I'd still end up in a final state. Now there are occasional examples when you use the pumping lemma where you actually want to do that, where your pumping number I that you want to use is actually 0, which means you actually are cutting the string down, finding a shorter string that should be accepted but actually isn't accepted. Sometimes going up doesn't work. Sometimes you actually have to go down. Sometimes you actually cut the loop out. So be aware that that equals is not a typo or a carelessness. It's true, and you can use it. All right.
I'm sorry.
Yeah.
Where going up doesn't work?
Yeah, there's examples where as you go up, well, the way we're going to use this pumping lemma is going backwards, showing that something doesn't have this property. To show that something doesn't have this property, you have to show that one of these i's won't work. And sometimes the only one that doesn't work is when it equals 0. Does that make sense?
Yes. That just means not going through the loop.
That's right. It means not using the loop. Cutting out some of this string, doing surgery, snip, snip, making it shorter. Because the string you started with does go through the loop. So if you don't use the loop, you're actually taking out a part of that string. Does that make sense? All right, I think we should do an example, which actually runs through this. But before we can do it, remember that we're not using the pumping lemma the way it's stated directly. Regular set implies pumping property. This is the pumping property. If L is a regular set, these 4 quantifiers represent the pumping property. We're going to use it backwards. We're going to be using it in the, or contrapositive, or whatever the term is. We're going to be showing that if something doesn't have this property, then it's not a regular set. We're using this to show that things are not regular sets. How do you show that this is not true? You have to put a not sign through all these quantifiers. It'd be one thing if I say, hey, 2 plus 3 equals 5. If you put a not sign through that, 2 plus 3 doesn't equal 5. It's easy. But sticking a not sign through this is a little ugly. It's not true that there exists an n equaling the states in the machine L such that for every string in L where the string is long enough, there exist 3 parts, that you could write it into 3 parts according to those conditions such that every I you wanted to could be pumped up and you always get things in the string. That's not true. Well, where do you actually pin it down to show that it's not true? In which part of this? So we're going to go through it and write down what this looks like when you push a not sign through it, and I'll put it on this side of the board. And then I'll erase this, and we'll use this side of the board to do an example. All right? Now, the good thing is that hopefully somewhere in your mind back there is a vague memory of stuff that you did in logic. And in logic, we mechanically showed how to push not signs through things like this. So I'll remind you if you forget. But if you push a not sign through a quantifier like this, it changes the quantifier from existential to universal. If I say there exists an n equal to the number of states in the machine for L, and then I say that's not true, that means for every number you try, it's not true. Okay, so when I put not signs through these quantifiers, it reverses their meaning. If I say it's true for every string in L, for you to show that it's not true, you want to show that there exists one string such that it's not true. Everything is going to get reversed. The propositions will get reversed, and the quantifiers will change from existential to universal. Okay, so let's write this out. This is the negation of the pumping property. And this is what we're actually going to be trying to show. We're going to do this mechanically, but in your head, logically, you could follow along as well. Pushing a not sign through here. So instead of there exists an n equaling the states in the machine for L, it's for any n equaling states in any machine for L. That's why when we did this yesterday, I told Chris and Donna to go home and tell me the machine they came up with and tell me the number of states. I had to handle it no matter what they told me. They could have told me an n that was equal to 7 or an n that was equal to 2052. My argument needs to work no matter what n they tell me. So we say for every n. That's the adversary's choice. The adversary gets to choose the universal things. I get to choose the existential things. Okay? If I have to handle a proof for every possibility, then it's the adversary that's dealing with it. And if I want to handle a proof for there exists, then I can just exhibit one. So for every single n, number of states in any machine you can come up with, there exists a string in L. I get to pick the string, because all I have to show is that there exists one. There exists one string in L whose symbols are bigger than n. Such that for every VWX where Z equals VWX, in other words, no matter how you split Z up into 3 pieces, for every possible way there is to split Z up into 3 pieces, I don't get to choose as the prover how to split it up into 3 pieces. It's Donna or Chris or whoever did the machine. They tell me where the loop is. I don't get to pick the loop. That's very important, because in the proof we have to be able to make our argument based on the fact that the loop might appear anywhere, and they just have to tell me where it is. So hopefully we can pick a string that's good enough that forces them, when they pick these 3 parts, to do it in a way that can't have too many different cases. The fewer cases we give them, the less flexibility we give them, the better. It's like a boxing fight. You want to give your opponent the least maneuverability possible. And the universal quantifiers are your opponent, and the existential quantifiers are you. Okay, so for every single way to split it up, where z equals vwx, and there's conditions on this, and vw is less than n, w greater than 1, same conditions as before. For every single way to split it up, there exists some I. You're going to have to exhibit some number bigger than or equal to 0, such that vwix is, and finally, not in L. It's my job to come up with a number so that when I pump up the string at the loop that they told me where it was, I get a new string which is not in the language, guaranteed, and it's supposed to be, so therefore they're lying to me. That means their machine doesn't satisfy the pumping property. That means their machine doesn't exist. That means there is no finite state machine and the set's not regular. This is what we're going to be using in the examples. And we're going to do 2 or 3 examples now and make sure everybody gets the idea, following this very formal structure in a more intuitive, logical way on the other side of the board. OK, questions about this? Who's getting this? Nobody? All right. Yeah, Todd.
We said V didn't have any loops. We formally said that. Doesn't matter.
We said we have
No loops in V. The W is the first occurrence of a loop. Where do we write that?
That's actually, it's not actually implied by the way I wrote it down. It is conceivable here that there are loops in V. It's this condition. I didn't prove this lemma, right? I just told you it was true.
Yeah.
But the reason this lemma is true is because the hard part is that VW has to be less than or equal to n. I know VW has to be less than or equal to n because I know there's going to be a loop that shows up there. And I'm saying that we'll call the first such loop W. So we're going to end on that. But it's possible that the person might actually be able to satisfy these conditions and have W be the second or third loop. That's true. So there's no guarantee based on what I wrote that there can't be any loops in V. But the fact that this is less than or equal to the n is implied by the fact that I know there has to be a loop, at least one, in n. But yeah, maybe you could have loops in V. That's possible. Yeah.
So in other words, if you can break it, it's a regular set?
If you can break the pumping property?
Yeah.
Yes.
Okay.
No. If you show that this pumping property is not true, then it's not a regular set. If it is a regular set, then you can pump the thing up over and over and over and over again. Right. But the converse of this, Joe, this isn't true. I can't just reverse this arrow. If you have a set and you show that it has the pumping property, you know that you can always pump things out of it, it doesn't mean it's necessarily regular. There are sets that are not regular that still happen to have the pumping property. So you can't always use the pumping lemma to prove that every single set that isn't regular actually isn't regular. I might give you a set that isn't regular that actually satisfies the pumping property, and you'll never be able to show the pumping property doesn't work because it really does work. So this is not an if and only if. It's not enough just to examine the pumping property of a set to decide whether it's regular. Most examples you'll see don't satisfy the pumping property, and it is enough, but some will occasionally. Yeah, I'll do an example where it does later on today. Yeah.
What part of this indicates that W is the first loop? I mean, in the writing of it.
I think that's what Todd was kind of getting at. The part that really indicates that is it's less than or equal to n. I'm guaranteeing the W is a loop, and I'm forcing my opponent to find that loop in the first n symbols. It doesn't have to be the first one.
It seems to me that
tell me any loop that occurs in the first n.
W to contain a loop, but that, for example, the loop might start 4 letters into W. That you're not.
No, well, I'm asking them to call W the symbols that are on a loop.
Well, you ask your opponent.
Right.
You
right.
ask them, but in this, the actual definition, I don't see anything that forces that.
There is nothing that forces it.
So it sounds like you're putting an extra restriction, giving your opponent an extra restriction more than what the property actually indicates.
Well, you know what? I won't ask my opponent anymore for the very first one. I'll just ask them for any loop that occurs in the first n symbols. That's enough too.
Actually, I'm not concerned that it is the first loop. I'm concerned that you're asking them specifically for a loop. because this W could contain a loop, but it doesn't. The way I'm reading this, W isn't only a loop. It might
No,
be
W is only a loop.
and something else.
No, it's not.
Why is that? What part of what you've written here specifies that?
This part over here, the part that I can pump it up, or the part that I can pump it up and it's still in the language. This says that there's some way to split this up into 3 parts so that I can pump up the middle part.
Okay.
That some way is going to be by finding that loop. And I can force my opponent, when they find it, to find it somewhere in the first n symbols. But you're not concerned about that. You're saying, where do I know that it's a loop? I know that it's a loop because of this consequence.
Right. Okay.
Okay? All right, other questions? I think we're ready to do some example. Okay, let's do the example that Dimitri wrote on the board yesterday, palindromes. 1L in palindromes?
Yeah. From the Greek, running backwards.
Yeah. Oh. All right. We want to show that the set of palindromes, those are things that read the same way right to left as they do left to right, that those strings, say over the binary alphabet 0, 1, that they don't satisfy this pumping property. Let's follow through our dialogue the way we did it yesterday and notice how it really goes along this set of criterion. I'm going to imagine that one of you went home and came up with a finite state machine that does accept palindromes, and I'm going to ask you how many states were in that machine. Or, according to this picture, for any n in the whole world that that person tells you, you've got to be ready for the next stage. Okay, so here's how I would write it. My opponent's machine has, let's call it k states. Okay? That's the for all. I got to be able to handle any number. Here I called it n, here I call it k. My opponent's machine has k states. You want to do it with an actual number like 50, or is k okay? K is all right? All right, my opponent's machine has k states. Now it's my turn. I have to show that there is some string in L that's longer than that number of symbols, k, such that all this stuff is going to work out. Now, what I want to do now is pick a bad string. Because when you first do these pumping lemmas, it's hard to look in advance to see what string you're going to need, because you're just getting used to it and you're a beginner. And you kind of hope you get lucky. So I want to get unlucky once, and then we'll get lucky the second time. All right, let's get unlucky. Let's come up with a palindrome that has at least k states. Here's a palindrome that has at least k states. 0 to the k, I don't know, k divided by 2, 1, 0 to the k divided by 2. Right, that's got at least k states. I put half k zeros on one side, half k zeros on the other side. I'll put a 1 in the middle. It's definitely a palindrome, right? Whatever the half of the k is, it got it on both sides. I got a 1 in the middle. It reads the same right to left. So I pick z equal to this. And I know it. I should make a little comment on the side. Note, z is in L. That is, it's a palindrome. It's a palindrome. Latin for running backwards.
Maybe the borrowed
Z is in L. It's a palindrome. And what else? And z has more or equal than k symbols. Okay. So I'm okay so far. I got through the second stage. Now it's my opponent's turn. Now I got to handle any possible set of 3 things that equal this string. So my opponent sets my z to VWX. Okay? I have no idea how my opponent is going to pick those VW and X. I have to be ready in my next stage for any possible way my opponent might have chosen these to split this string up. Now you play the opponent. The last stage in this game is I'm going to try to pump up this middle part that you, the opponent, is going to pick. I'm going to try to pump it up and get something that is not a palindrome. VW to the IX, that's not in L. That's going to be my job in the very next stage of the game. We're in the penultimate stage of the game. You get to pick the VW and X to make me suffer. So it's this big opportunity. What do you want to pick? What if you pick the W? So my opponent picks V to equal 0 to the K over 2, W to equal 1, and X to equal 0 to the K over 2. That's perfect. Well, let's check if that's reasonable. Remember the conditions my opponent has to abide by? There's a couple conditions they have to abide by. They can't just split it up randomly into 3 parts. Because I'm asking them, tell me the first loop you came up with. That's what I'm asking them for this W. And the only condition that I can impose on them is that I don't know where that loop is, but I know it's got to happen in the first n symbols, or excuse me, the first k symbols. The VW part has to be less than or equal to k. Well, this VW part is certainly less than or equal to k, right? It's about k over 2 plus 1. So they're okay so far. And they gave me a real loop. The W is bigger than or equal to 1. And it's actually the string 1 itself. So you didn't do anything wrong here. You came up with a perfectly reasonable way to pick VW and X. And I'll write that down. VW is certainly strictly less than or equal to k, and the W is certainly greater than or equal to 1. Note. That's your opponent note when you send it to me. I go, okay, fine. And now I look and I go, crap, I'm dead. Because whatever I use for I, no matter how many times I pump up that W, I get a palindrome. It does pump out. It does satisfy the pumping property. So this whole attempt at showing that the pumping property didn't work failed. I made my move. Sorry, you made your move. I made my move. You made the last move in the game. Checkmate. I got killed. Every single I try doesn't work.
Can't use that W to some. Does it have to be the middle value?
That's the only one I'm allowed to use. That's the only one I'm allowed to pump out. Well, you guys might want to help me if you were bad opponents, and make the W easier. But you want to be my opponents. You want to pick this W to make my life as hard as possible. So what I did wrong here is I didn't play this game well enough. I started with such a bad move that you guys could checkmate me even though I should have won the game. I should have succeeded in this proof. You made me fail in this proof not because I really can't succeed, but because I started so badly. This is tricky, but it's just technical. It's not really deep. It's just technical. You have to show that this property doesn't hold, and in order to do it, you got to make the right choices along the way. Just because you make a wrong choice doesn't mean there wasn't a better choice to make. So I made a bad choice. I picked a bad string to start with, and you guys won. That doesn't mean that the pumping property necessarily holds. It just shows that this one attempt at showing it doesn't hold didn't work. I'm going to pick a better string, and I'm going to nail you guys. Okay? Seth, what are you thinking about? Waiting for my better string? All right. Waiting for my better half here. Okay, let's do this with better string. Instead of this, let's pick what actually might seem like a more natural string. 0 to the k, 1, 0 to the k. Let's do that string. That might have been the first string you might have picked. So my opponent has to set 0 to the k, 1 to 0 to the k equal to VWX. Now, can you guys pick W equals 1 now? Now I nailed you down because I made the first case symbols have all zeros in them. And you have to pick your VW in that section. The VW's got to be less than or equal to k. This no longer is a possible choice for you guys. You can't find the loop in the first case symbols and have the loop be a 1. Because there is no 1 in the first case symbols. The only thing you could possibly do, and I will note this, my opponent sets this equal to VWX, and I note that the W equals 0 to the m for some m between 1 and k. No matter how you split it up into 3 parts, I know that the W part is going to be all zeros. And that's what I'm noting here. It's some number of zeros that's more than 1 and less than k. Everyone agree? I say, where's that first loop? It's got to be in those first case symbols. You can tell me how big it is. You can tell me where it is. But whatever you tell me, it's going to be all zeros. OK. So at that point, it looks like some of you got confused. Let me stop for a second. All I did now is notice that if you split this into 3 parts, you as my opponent, the middle part's going to be all zeros because I got you nailed in the 0 to the k section. And now here's how I'm going to finish the game and win. I'm going to say let I equal 2. Pump this up, that means 1 extra time. Here's v, w, 2x. What does this equal? VWX was equal to 0 to the k, 1, 0 to the k, right? That's my z. It used to be equal to this. If I pump up an extra w in it, how many extra symbols, what symbols do I get? I get m zeros. So it looks like this now. 0 to the k plus m, right? It's in that section, followed by a 1, followed by 0 to the k. And m is definitely bigger than or equal to 1. And that's not a palindrome, because the 1 is in the middle is shifted off center. And I conclude, which is not a palindrome. And then I say QED, I'm done. All this is necessary to show that the pumping property doesn't hold for palindromes. I'm going to stop for a minute for questions. Gary, got a question?
Hence, palindromes are not regular sets.
Hence, palindromes are not regular sets. Yes, but that's not a question. That's just a correct statement. Yes, you're right.
My intonation didn't indicate.
No, you got to be a little more.
Not a regular set.
There you go. More confidence. Like that. No, that's good. Good. Exactly right. We finished with this. Hence, palindromes are not regular sets. Hence, a set of palindromes is not a regular set. Now I got it. Erica, okay? Yeah. Tom, good. There's a good friend of mine who teaches like this. And I actually like it, but I rarely ever do it. I think it really actually works. At the end of anything complicated that he ever says, he stops. And he goes around the room, and he looks. And it's really tough if you're in the class, because you can never take a minute to space out for a second. He goes, Michael. You get it, Michael? You really get it?
Person in the room?
Anybody who doesn't have an amazingly confident look on their face. Andrew, make sense? And then if there's any hesitation on the, yeah, I definitely get it, he explains exactly what he thinks you don't get. The lectures can go on a long time, but it's...
Doesn't that just encourage your students to lie?
No, but it's very hard to lie about that, because you never know if he's going to ask like a follow-up question. You never say, I definitely get it, because then I'll say, okay, well then, if I did this, does that make sense? And they go, I didn't really mean it. I'm sorry. I was thinking about dinner tonight. Sorry. You can't lie. The bacon brownies. Okay. Let's do another example. And then you guys will be more involved with this one, and you'll get a sense of how it works. I did this. Look, this is hideous. It's hideous because if I had you read this, there would, unless you're good at reading math, you wouldn't get the idea behind it. But this is how you write it up. When you write your problem set up, either write very good English paragraphs describing a dialogue with an opponent that you clearly explain the give and go and the give and take or whatever, or write it up like this mathematically, where, let w equal 0 to the m because it's got to... Be very careful. This is a formal way. Sometimes if I don't do one example like this, somebody says, well, I get the idea, but I'm not really sure where to go from here as far as how to write it. And the answer is that's it. It looks something like that. Let's do another example. Yeah,
Is this like one of many lemmas that lets you attack?
There's different kinds of pumping lemmas, but there's only one, but they're all the same idea. Basically, regular sets have these loops, and they regularly can be pumped up. And anything that can't be regularly pumped up is not a regular set. See, unfortunately, there are things that can be regularly pumped up that are still not regular. So this is not a characterization of all the regular sets. In fact, it's very hard to get an if and only if. You know what? There is an if and only if for regular sets with a single alphabet symbol for zeros. There is a characterization for all languages over the single alphabet 0 that are regular. And that's a very linear kind of characterization. In fact, I think it's probably one of the extra credit problems I might have given you on one of the homeworks. There you can actually say a set over just the alphabet 0 is regular if and only if this, and explain it. You know, it's basically if and only if it looks like this. More or less things like this. You know, some linear combination of zeros, plus finite unions of things like this, basically.
You can't write these as regular expressions.
Oh, you can write.
Palindrome.
No, you can't write them as regular expression. Right. Right, exactly. Right, palindromes require some kind of recursive description or something different than a regular expression would let you do.
What is it about it that doesn't let you write it as a regular expression?
Well, let's try to write it as a regular expression. How about this? That's a start, at least, right? That's my first bad attempt. That makes sure that if there's a 0 in the front, there's a 0 on the end, or if there's a 1 in the front, there's a 1 on the end. Is that all the palindromes? All the 2-character palindromes, right. This is the set of all palindromes where you're just going to look on the first and last symbol. But if I want the first 2 symbols and the last 2 symbols to match, it looks like I'm going to need a union of 4. You know, 0, 0, anything, 0, 0, 0, 1, anything, 1, 0, 1, 0, anything, 0, 1, 1, 1, anything, 1, 1. Look, I know that's a dumb way to do it, but I don't see any better way, and we just proved actually that there isn't any better way. There isn't any regular expression that can do palindromes. And that's an attempt to try, and we'd get stuck if we kept trying. Does that kind of give you a sense? I hope. All right. Should we do another example? Let's do another example. Yeah, good. There's one example I definitely want to do, but I want to leave it for last. Maybe I want to do a little easier one right now. Let's see. Should I do the square one again? Was that worthwhile? Should I do that again more formally? Yeah? Let's do the square one again. This is a set of strings just over the alphabet 0 that has a square number of zeros. So it includes the empty string, a single 0, 4 zeros, 9 zeros, 16 zeros, 25, etc. We want to show that this is not regular. Okay?
How does it include the empty string?
Because the k could be 0. So 0 to the 0 means no copies of 0.
Okay.
So that's the empty string. What?
Isn't something to the 0?
If it's in numbers, something to the 0 is 1.
Okay.
But the 1 is kind of like the identity for multiplication. The identity for string operations is the empty string. So when you combine one string with the empty string, you get the same string. When you multiply something by 1, you get 1. Now, it has the same role. In exponentiation to the 0 should always give you the identity in the structure that you're dealing with. And the identity here is empty string. It's a good question. It's the basis of deep mathematical algebra. Yeah. Good. All right, let's go through this thing again. I want you guys to try. what's the process? What do I write first? Pretend you're writing a formal proof. What do you write first? We want to show that this is not regular. Claim 0 to the k squared is not regular. How do you write down in math blabbering that your opponent has chosen an n for you?
The machine has so many states.
Right. Right. And the way we normally write that is, let n be the number of states, or let k be the number of states. The word let is overused in mathematical writing. Let's not use k because I have k here. So let n be the number of states in a hypothetical machine. For 0 to the k squared. Okay. That's step one. That's this top step. Now what? Now what do we write down? Right, we pick a string. Well, in this case, we're going to be just fine picking a very simple string. We're going to pick 0 to the n squared. We're going to note that this is definitely in the language. We have to pick a string in the language. We want it to end up in a final state. 0 to the n squared, which is in the language, and which is bigger than n symbols. It's got n squared symbols. It's a lot bigger than n symbols. Okay, that we have to make sure about. Now I've gotten up to here. So far we got no trouble. Next step. The opponent does something, so we're going to use that let word again. Let 0 to the n squared equal VWX, where VW is less than or equal to n, and W is greater than or equal to 1. Right? We have no idea what the V's, W's, and X's are. We just know that these conditions are true, and we know that 0 to the n squared is built up out of those three pieces. We use the word let to show that we have no choice over it, to show that it is a universal kind of quantifier. And now we have to pick an I and pump it up. And we're going to get lucky, and I equals 2 is going to work again. We're going to choose, I'm going to write I pick instead of let. I pick I equals 2. UV2, sorry, VW2X equals. Tell me what it equals. If I pump up W twice, then how many zeros are in that thing? It'd be nice to know how many zeros were in W, right? So maybe it's important to realize, okay, you don't always have the words for what you want to say when you're writing things mathematically. And whenever that happens, you backtrack and you kind of throw in a definition to make this line a little easier to write. So let 0 to the n squared equal VWX, where these things are true, and let the size of W equal m, strictly less than or equal to n. Just so it has a name. From now on, we can call it m. The number of zeros in W is m. If I had written this first, you'd say, what the heck are you calling it m for? And even now I don't have to. I could just write, bar W bar. But it's nicer just to indicate that it's important. So now we can write how many zeros this is. How many would it be? 0 to the k squared plus, no, just plus m. Because VWX was k squared, and when we pump it up to 2, we're only getting one more copy of W. Okay? What's that?
1 squared.
It's, oh, okay. Thank you. Thanks. N squared plus m. All right, so now what? I picked I equals 2. I said what VW2X equals. I have to convince you that this is not in my set, that it's not a square. So now I need to go to a new, I'm going to erase this. We don't need it anymore. I'm going to go to a new board and convince you that 0 to the n squared plus m can't be a square. I claim 0 to the n squared plus m is not equal to 0 to k squared for any k. Okay, it's not a square. N squared plus m is not a square. And here's my proof. N squared plus m is strictly greater than n squared. How come? Because m is at least as big as 1. So it can't be equal to n squared because it's bigger. And I'm going to also claim that it's strictly less than n plus 1 squared. So it can't be a square because it's stuck in between two squares. Who does that song Stuck in the Middle with You? Is it the Eagles?
No.
Don't think so.
No, it's not, right? Doesn't matter. Here we are, stuck in the middle of these two squares, and this is bigger than this one, and it's got to be smaller than that one. This part is true because m is bigger than or equal to 1. Why is this part true? This is n squared plus 2n plus 1, and m is definitely less than or equal to n, so it's certainly strictly less than 2n plus 1. Therefore, this is true. Therefore, I conclude n squared plus m is between two squares. It can't possibly be a square. I write a little English paragraph. I say QED. I'm all done. It's a lot of work, but it's a powerful tool, and the idea of it is very straightforward. Clicking? Good. All right. And you'll notice, well, what trick do you use? Like here we picked 2, and the trick was that it was in between two squares. Before, we wanted to pump up a part to make it not look like a palindrome. And if you're thinking, boy, is it always something different every time? Yes, it's always something different every time. And yes, you have to look in advance, and the best way for a beginner to try is try something, let the opponent work as hard as they want, see if the opponent wins, and go back and fix your try if it didn't work. And when you get better and better, you'll be better at picking it in advance. And if you can't get it after a couple tries, ask me and I'll tell you. That's always a good way. Okay. Questions about this?
And we know it'll work because the problem says use this because it can't be right. But you could be sitting here and at some point go, well, maybe it really is a regular set.
Right. We're going to do that. No, maybe it really is a regular set, or maybe it really has the pumping property. Even worse, maybe it really has the pumping property and it's not a regular set. So I could sit here all day long and never succeed with this, even though the set happens not to be regular. And that happens. We're going to do an example in just a second. Okay, can I erase this one? Let's do another example. What about all numbers that are not prime numbers, that are composite numbers? Now, in doing this, we can go through that, the same kind of thing. Let's say somebody picks an n. I don't know how many states that is. Maybe their machine has a prime number of states. Maybe it has a composite number of states. Whatever number they pick, what if I just pick 0 to the 2n? I know that's composite. I know it's bigger than the number of symbols they have in their machine, so I'll try this. Everybody with me so far? So this is my z. And the opponent, I'm not writing it out informally this time. I want to just make more sense out of it. So the opponent splits this into 3 parts, VWX. The W part's got to be somewhere in the first n symbols. Now you're the opponent. Nail me down so that no matter what I choose, this is going to end up staying composite. That would make it hard for me. What W do you want to pick? Or we can turn the board around. I'll be the opponent. You be this guy. In a second, I'm going to be trying to taking the 0 to the 2n and then adding multiples of this W to it and hoping to get something that ends up being prime, that ends up being not composite. How am I going to do that if you make this W equal to 2? 2 zeros. If you make the W equal to 2 zeros, then I'm always adding 2 zeros to it. 2 zeros to some even number. I'm always going to get an even number. I'm never going to get a prime number. I can pump up W to my heart's content. I'll still get an even number. The answer is that I'll never succeed, and you'll kill me if you pick W equal 2 zeros. And I can't pick a better string because you can always just find W equal 2 zeros. Maybe I should have picked 3. Well, then you could pick W equal to 3 zeros. Whatever I do, you're going to nail me in the next step. We could play this game a lot, and I would lose every time. And in fact, if you go back and do it the forward way, you can prove that 0 to the k, where k is composite, that it does obey the pumping property. You can always find some little part in there which you can pump up and keep getting composite numbers. But this is not a regular set. So here's an example of something where the pumping property happens to hold. That means I'll never succeed in showing it's not regular using the pumping property. The pumping property happens to hold, but it's still not regular. So you give up, but you still have to show that it's not regular. So there's a related technique which is very easy to do. Let's say I already showed to you, because you're going to do it on the homework, that the complement of this is not regular. On the homework, you can use the pumping lemma to show that 0 to a prime is not regular. You can get a hold on that. It would take me 20 minutes to go through the answer, and maybe we'll do it as a review, but I want you to try that one on your own. It's a homework problem. You will do it. You'll use the pumping lemma. You will show that 0 to a prime is not regular, and you're done. Now, when you're done doing that, how do you then conclude that 0 to the composite is not regular? Not by using the pumping lemma again, because it wouldn't work, but by noting that these are complements of one another. So if this was regular, then that would have to be regular also. Therefore, it's impossible for this to be regular. Does everyone get that idea? That's the idea of closure. If you know that regular sets are closed under complement, and you know that the complement of the set you're dealing with is not regular, then the set you're dealing with is also not regular. If I know that 0 to the prime is not regular, and I'm not sure about 0 to the composite, and the pumping lemma isn't working, then I can say, well, I know it can't be regular anyhow, because if it was regular, its complement would have to be regular too, and I showed before that its complement wasn't regular. So it's kind of a proof by contradiction using closure properties. And you can do this with complement or reverse or any of the closure operations. It expands the repertoire of what you can show is not regular by a lot. So closure is not only used in a positive way, it can be used here in kind of a negative way to show that things aren't regular sets. All right, questions about that idea? It's another good example of this. Here. We showed yesterday that 0 to the n, 1 to the n was not regular. Right? We used the pumping lemma to show that. We could do it again formally today. Let's assume we know that that's not regular. How would you show that an equal number of zeros and ones are not regular? That means mix them up all you want, but there have to be an equal number of zeros and an equal number of ones. They don't have to come first zeros and first ones. Well, actually, you could do that with a pumping lemma, and it wouldn't be too bad to do it. But you could also do it with this trick. Equal zeros and ones intersected with 0 star 1 star equals this. Does everyone agree? If you take all the strings that have an equal number of zeros and ones, and all the strings that start with zeros and end with ones, and you say, what do they have in common? They have these in common. The strings that start with zeros, ends with ones, and have an equal number of zeros and ones. This equals this. But are regular sets closed under intersection? They should be. They are. Therefore, you know this is regular. You know that's not regular. So what are the choices for this guy? Not regular. If this one were regular, then the intersection of the two would have to be regular. Everyone understand that? It's the same idea. Here we're using closure over intersection. It gives you a tremendous variety of ways to show things are not regular. The pumping lemma is a direct way, and then these closure properties is an indirect way. Keep in mind here it's really not necessary. If somebody wants to show that equal zeros and ones are not regular, I can just come up with a string of equal zeros and ones. Here, 0 to the n, 1 to the n. That's the string I pick. And then I'll win the argument just like I did with 0 to the n, 1 to the n. And that's kind of the intuition behind what Chris was saying the other day about, oh, if it's a subset of the thing, then you have to be really careful when you say stuff like that. It's almost right. Anyhow, that does that example. I want to do one more quick example of this intuitively, and then I'm going to let this topic go. Are there questions? All right, last example. Remember yesterday we described how to turn finite state machines into binary. We did it in our own peculiar ADU way. We decided that the number of states would be listed by the number of zeros in the string, and then a separator of a 1. And then we start with a start state and say where we went on a 0, we went back to state number 1. And then where we went on a 1, we'd go to state number 2, then another separator. Then we move on to the next state. On a 0, we go to state 2, and on a 1, we go back to state 1. Another separator. And then we add on all the final states. Number 2 is the final state. And I think we put a double 1 here before the final states, right, to make this final separator. So this 0 and 1 string represents that finite state machine. The number of states, the transitions on 0, 1 for the initial state, the transitions on 0, 1 for all the other states, and then whatever final states you have, listed with 1s in between them. We did this for diagonalization idea, but we're going to use it again right now. This is a legal finite state machine. Is that a legal finite state machine? No, because I'm supposed to have 3 states, and I didn't say what to do with any of the states except for the first one. I need to have 2 areas, 1 for 0, 1 for 1, for each of these 2 states. 1, 2, and then a double 1. Here I'm supposed to have 3 of these double areas. I only included 1. There's lots of strings that are not legal finite state machines. There's lots of strings that are legal finite state machines. If I gave one to you, you should be able to figure out whether it is or not. You could write a program to do it. Can you make a finite state machine to do it? Can you write a finite state machine that recognizes one of its own kind? Not whether it's a fancy one of its own kind that actually accepts itself or not. Forget that stuff. Can it just recognize another finite state machine? Forget I'm supposed to recognize which of the humans in this room are emotionally healthy. I just have to recognize which one of you are actually humans. Okay? I don't have to know anything about you. I just have to be able to distinguish between you and a chair. So can a finite state machine do that? Can it distinguish between strings that are finite state machines or strings that are not finite state machines? Everyone understand the question? What do you think? Is this set regular or not regular? Not regular, because finite state machines can't do squat.
Is that the mathematical?
I think I must have told you this story, but it reminds me of this course I took in college where we were doing psychiatry with linguistics. It was a semiotics course. I told you this story, right? No, I didn't tell you this story? I'll tell it really fast. Anyway, all year long, you go to the class and the doctor plays tapes of crazy people. And you listen to the interview between he and his associates and these crazy people. And when you come in, I mean, this is a kind of a way to analyze crazy people. So when you come in, you have to kind of get indoctrinated into this way of listening to make, you can't just go with your gut instinct. You got to be trained to talk in the right language. So he would stop after the first lecture and he'd say, "What do you hear?" And I was a freshman in college. What the hell do I hear? I don't know. It doesn't make any sense at all. I don't get it. So he would do "What do you hear?" a dozen times. By the end of the year, I had an idea of what he meant by "What do you hear?" You had to listen to the actual words, whether it was concrete thinking, what the metaphors were. It's very complicated. You got a sense of it. So toward the end of the year, we're listening to one interview with a child, and the child is just out of this world. It's amazing the kind of things this kid is coming up with. Really, really interesting. And I'm listening, and I'm really getting fascinated, and we're all done, and the doctor goes, "All right, so what do you hear?" And we're going around the room, and everybody's come up with theory after theory and and I actually had some ideas, and I'm sharing it, and I'm waiting, for the answer. What does the doctor say? So he doesn't say anything. So finally, somebody in class says, "Well, what is it, doctor? I mean, what do you think about this kid? So he looks at everybody and goes, oh, I don't know, he's the craziest kid I ever met in my life. I couldn't stop laughing. I'm thinking, oh, there's one semester down the drain. Oh, God. So where was I? I forgot where I was.
Finite state machines that can't recognize.
Oh, yeah, they can't recognize themselves. Right, right. So, so you think it's not regular because finite state machines can't do squat, right? So
Not to get too technical.
that's right. So let's do this more formally. Convince me that it's not regular by doing the pumping on, but now you guys have to do the pumping. I'll be the adversary. All right. So I provide the number. I provide you with an n. So let n be the number of states in the machine. I have a machine that recognizes finite state machines, that recognizes legal binary strings that are finite state machines. N's the number of states in my machine. I got to stop talking while I write. Okay, now it's your turn. You have to come up with a string. You have to come up, I'll remind you what you have to do. You have to come up with a legal finite state machine, something that I should accept, that has more than n symbols in it. Everyone agree?
That has more than n?
Yeah, it's got to be longer. That way it should be able to be pumped up. Yeah, Chris? You have a-
If we have n zeros and then n pairs of inputs and a couple of valid states at the end, we have.
Yeah, I mean, I think Chris has the right intuition. So let's take Chris's idea and look ahead. If we just start with n zeros at the beginning, make it something with n states in it, and then throw any garbage at the end. Later on, when you guys are going to pump this up, no matter how I split it up, my W is going to be stuck here in this section. And then you pump it up, and what happens? You get more states in the machine, and nothing changes out here, and it won't be a legal finite state machine again. It's actually a really easy proof, because this particular encoding scheme that we used is so specifically counting oriented. It counts the number of states, and then something else later has to have that many. It's almost like 0 to the n, 1 to the n. I should point out there are other encoding schemes for finite state machines. I could encode them so that any binary string represents some finite state machine, and then it would be easy to accept them all, just 0 plus 1 star. Everything's a legitimate finite state machine. So this really depends on the encoding scheme. But let's go through the details now. So 0 to the n, let's just put in pairs of zeros, n pairs of zeros. N pairs of zeros. And how about no final states? Who cares? All right, so you give me this string. And I split it into 3 parts, VWX. And no matter what I do, the W is going to be stuck here in the first n symbols. So the W is some number of zeros. And you can pump it up how many times? Any number, 1 time. So this becomes 0 to the n. Let's call the W's that m again. 0 to the n plus m. This stuff is exactly the same. And that's not legal because here we have n pairs of zeros and m plus m states in the machine. Everybody get that trick? So our encoding of finite state machines are too hard for finite state machines to accept. So it's not surprising that the finite state machines that actually don't accept themselves are also hard to do. I mean, this is hard. Good. By the way, there's a Turing machine that could do all this. The higher levels understand everything about finite state machines. They're a superior intelligence. They can stare at the finite state machines and not only know what they are, but actually simulate them and answer questions about them. They're just not smart enough to answer questions about their own kind, but they can do everything about finite state machines.
You do reach a point, though, where you can know about yourself. I mean, I can
Maybe
write
you. Yeah.
I can write a Java program that can tell me if something else is a Java program.
Yes, if something else is a Java program, you can. Yes.
So there is a point at which you cross.
For the Turing machine level, Turing machines are powerful enough to recognize their own kind. That's what compilers are. What they're not powerful enough to do is recognize any interesting properties about things of their own kind. They can't, for example, say, here's another Java program that never infinite loops, or here's another Java program that accepts exactly 5 inputs. Or here's another Java program that, that doesn't accept anything. It can't do that.
Why not?
We'd have
The
to,
first
we're going to
part
prove
does,
that.
But the second part, the second two parts, being able to recognize the number of inputs, doesn't seem right.
Well, because what would you do? You'd have to run it on all possible inputs and say it just, you can simulate it, but it could just go forever and you'll never know your answer. If the answer is yes, you'd get the answer yes.
No, it's within a particular language. There's always going to be a particular way to determine. I mean, oh, the number of, oh, sorry.
The number of arguments. But
Not the number of arguments, the number of different inputs that would be accepted, and the thing stops and says yes, yes, yes.
Who is this?
That's okay. Let's do one little thing and then we'll quit today.
Can I ask you a quick question?
You may.
It seems to me that we've certainly proved that with this particular encoding scheme that finite state machines can't recognize each
Right.
other. But have we proven that there's no possible encoding?
No. In fact, there's an easy encoding scheme that makes them recognizable by themselves. I'll give you one. Why don't we use this encoding scheme that we talked about for a minute? Every finite state machine has a binary number associated with it, right? Let's order all the finite state machines according to size. Okay, so the first one is the smallest one of these string, the smallest number. And I will now renumber all these finite state machines. I'll have the smallest one, I'll call it 0. And the next smallest one, I'll call it 1. And the next smallest one, I'll call 2. So now every single finite state machine has a binary number, and every single binary number is now taken care of. So every binary number in the world now has a finite state machine associated with it.
Wouldn't there be two different machines that are the same size?
I don't think so. No, because I'm taking all the finite state machines, you come up with its binary number, and just sort them for me. Put them in order, and then renumber them from 0 to infinity in that sorted order. So now they have new labels. And every single number from 0 to infinity is going to be used as a label. So
Is that encoding or is that just labeling though? Because if you give me some super long string, I can't decode it. I have to go look up in an index.
That's decoding. Admittedly, it's may not be a formula. It might actually be a table, but it's computable. It's perfectly fine from computability point of view. And it's not a wonderful encoding. It's not quite as pretty and simple as this. But I certainly could go through this idea. You give me a string. I reconstruct all the possible finite state machines. I make a table. I count down as many as the string you gave me, and there's the one I want.
The table is going to be infinitely long.
Yes, it is.
And that table is actually an auxiliary memory. So we're no longer really in finite state because we're using an infinite memory.
Now, I'm talking about a program doing it right now. I'm talking, as far as actually figuring out which one it is, a computer program would have to do it. But a finite state machine is smart enough to just recognize whether it's really one or not, because everyone is. So here's the finite state machine that recognizes legal finite state machines in that encoding. It's just that, right? So if you're thinking that's kind of a trick, and it is a trick, but it's normal to make encoding schemes so that every single encoding means something. I could also say this. Here's an even easier way to do it. Use the same encoding we have, right? Any binary string that's not a legitimate finite state machine, I define that to be the finite state machine that accepts nothing. I define that to be this machine. So now every single encoding has a meaning as far as a finite state machine goes. It's just semantics.
So if we can do this, then, I mean, how does that jive with your earlier statement that you can't build a finite state machine that can recognize other finite state machines?
You can, depending on the encoding. But you can't build finite state machines that can know anything about the other finite state machines. We did prove yesterday that you can't have a finite state machine that accepts other finite state machines that don't accept themselves. That's impossible, no matter what encoding scheme you use.
Right.
So this level, it does depend on the encoding scheme. And it's why compilers work and stuff.
And this encoding can't actually identify the
No.
machine.
Finite state machines are not smart enough to identify which one. Right.
It's been encoded.
Oh, yeah. Ugh. Can't do anything. Okay. All right, other questions? One more topic before we quit today. This is a short topic, and it's self-contained, and I want to squeeze it in today because I want to start tomorrow scratch on minimizing finite state machines and get that finished. And this topic connects the trio of regular expressions, deterministic finite state machines, and non-deterministic finite state machines with right, or let's just call them linear grammars. It adds in a new idea, a new way of looking at sets, a grammar way of looking at sets. As the levels go up, the grammar way of looking at a set becomes at least as important, if not more important, than the machine way of looking at a set. And it really is a different way to look at a set. Seeing it at this level of finite state machines, it's not always presented at this level. It's usually presented at the next level where it relates to compilers and describing programming languages. But it's really worth seeing it at this level because it's so easy and transparent at this level to make sense out of it. The best way for me to explain what a linear grammar is not to define it, but to show you an example. So here's an example. Here's a finite state machine, the one that accepts, what does this one do again? Odd number of ones. Okay? Even ones, odd ones. We accept all things with an odd number of ones. I'm going to create a grammar. A grammar is a formalism that doesn't accept or reject things. It generates things. Anything it generates can be spit out, and the things that get rejected by this machine, the grammar won't be able to generate. So the things this machine accepts, the grammar will be able to generate, and the thing the machine rejects, the grammar won't be able to generate. Let me show you what I mean. You have a start symbol. Call it A. Same as this. And you can generate symbols that this machine can accept. Generate strings. You could start with a 0. What do you want to continue with if you start with a 0? You could continue with a 1, but we'll do that next step. You want to continue with something that A can generate again. You could also generate a 1 and then continue with a B. That's all you can do in state A. Generate a 0 and then continue with something else that A can generate. Generate a 1, continue with something that B can generate. If you're in B, you can generate a 0 and stay in B. Or if you're in B, you can generate a 1 and go back to A. Let's use these are called productions. Let's use these productions of this grammar to generate some strings. We're going to get stuck at the very end, and then we'll have to finish up this grammar. Let's start from the start symbol. One of the symbols is indicated as known as the start symbol. It's usually written as S for start, but we used A. Okay, but we have to start from A. So we start from A. What I'm going to write here on the board is called a derivation. A sequence of substitutions in the grammar, one after the other, creating a long derivation. We start with A going to 0A. And now I can substitute for this A. Why don't we substitute 1B for this A? These are the rules. This is a sequence of the rules being applied. So 0, 1, B. Let me stop for a second. Who understands so far? Yeah? I'm starting here. I made a substitution. I continue my substitution with A turning into a 1B. And now I continue with a substitution from B. Who can give me a legitimate next step in the derivation? Say it. Who's saying it? Say it again, Michael.
0, 1, 0.
0, 1, 0B. That means the B turns into a 0B, and that's OK.
Don't we need a terminator?
Oh, yeah. Absolutely, Doug. Right. We're going to get stuck because we're not generating anything. We always have these capital symbols left there. The capital symbols are called non-terminals. They should not be there at the end. No terminal. They shouldn't be there. The terminal symbols are the symbols in the alphabet. They should be there. The 0s and 1s are used as terminal symbols. Capital letters are conventionally used as non-terminal symbols. For this to be a grammar that generates anything, we have to have some way to kind of get rid of the capital letters. Well, which way corresponds to what this machine is doing? The B can disappear. The B can generate nothing, and then we accept whatever we have actually generated symbol-wise to get there. B can go to the empty string. Now that's a grammar.
I didn't understand that.
What we're doing here, if you follow this through, A going to 0A, that does this one. and then A going to 1B, that's this next one, and then B going to 0B, that's the last one. So if you follow that through in the machine, it's 0, 1, 0. Now we're ready to continue from B, but B is an accepting state. So we should be willing to accept 0, 1, 0. As far as the grammar is concerned, we should be willing to generate it. We should be willing to have it sit there on its own without any more capital letters. So anytime you arrive at a final state, you should be willing to stop. The way to make that stop occur in the grammar, at least going from left to right in this way, is to have that capital letter go to an empty string and disappear. So the last step would be 0, 1, 0. This is a derivation of the string 0, 1, 0, starting from the start symbol A, going through all these intermediary steps are sometimes called sentential forms. Well, fancy names, but if you understand the idea, you don't need the names.
What are the transitions called? The mappings?
Productions.
Ah, yeah.
Productions. All right, so this is called a linear grammar. Here's a definition of a linear grammar. It's got a single capital letter on the left of every production. And the right side is a very special form. The right side has a single terminal symbol and a single non-terminal symbol and a single capital letter. Starts with a terminal, ends with a non-terminal. Every single production looks like that. This kind of linear grammar is sometimes called a left linear grammar. Actually, I'm not sure if it's called left or right because it depends on the book, but I call it left because the terminal comes on the left. Okay?
Now, this one looks like it's assuming that we're going from a deterministic finite state machine. If we went from a non-deterministic, we might theoretically have multiple.
Actually, the same mechanical procedure. Well, first of all, let me note what you're kind of understood implicitly. This was actually not just an example of a grammar. This was an example of how to take any finite state machine and turn it into this kind of grammar. And I picked this finite state machine, but we could have done this with any finite state machine. I interpreted the states as non-terminal symbols, and the production as transition arrows, and final states as empty productions. So what Doug asked me is, what if I had started with a non-deterministic machine? Could we have still done this? And the answer is yes. It works just the same way, because the ORs in the interpretation that we have in our machine end up being ORs in the interpretation of our grammar.
So it just be an additional row in the production?
Mm-hmm.
Okay.
It's perfectly fine to do this transition from a non-deterministic machine. Of course, you could always convert the non-deterministic machine to a deterministic machine first, and then do this, but you don't even need to. Questions about this conversion and connection? So this should convince you that if you have a deterministic machine, we know about this. These are all the same. Now we know a deterministic machine can be made into a left linear grammar. How do you know that a left linear grammar can be made into a machine? If somebody gives you something like this, how do you turn it into a machine? Yeah, it's really a very one-to-one thing. You look at the productions, you make states out of the non-terminal symbols, and you just go in reverse. Like anything that I say, oh yeah, you can just do it, it might be a little bit tricky. So maybe we'll do one example of that and we'll quit today, just so we can see how it goes backwards and see if there's any pitfalls in the reverse procedure. Okay?
Every except state goes to that like that bottom line.
Yes, every except state would have this. By the way, there's another way to finish up here. I mean, you could also just have B going to, well, this is the easiest way. This is the easiest way. It's clear.
Mark the start states, especially.
Yeah, we'll use S normally for the start state. So normally I change this A to an S. Yeah. We're going to talk about grammars in much more detail. This is a special kind of grammar called a context-free grammar. Context-free grammars have single non-terminals on the left. They can have anything on the right. This is a special case of a context-free grammar where the right side is constrained. So if context-free grammars are over here, then inside them are linear grammars. ones where the right side looks like this. There's also, by the way, this is a left linear grammar. There's right linear grammars. There's a homework in the problem set in the next homework about that. You'll see that. But left linear and right linear, take my word for it, now are the same. You can convert one to another. And you convert them both to machines. Let's do an example now where I give you a grammar and we turn it into a machine, and then we'll quit for the day. Why don't you make up the grammar? So I won't be fooling. So you can have anything on the right as long as it's a terminal or a capital letter, or a single terminal is OK too. All right, so let's just make one up at random. S goes to... You need a terminal first. I guess you could do... You could do that. We could have that, but it's usually not in the definition. Usually it has to be a terminal and then a... Actually, if we allowed that, we could get rid of all those unit productions. We don't need them. Yeah, like S, this. This is officially not allowed in a left linear grammar, but I think we could get rid of it if you had such things. This doesn't really add much. This is just like a replacement of one letter for another. So I think we can get rid of these. But anyway, it's officially not allowed. So let's start with some. Yeah, 0A is fine. Next one. All right, 1B.
A goes to 0. B goes to 1.
We're too slow. E.
We got enough. Let's here. How about A goes to 1, B goes to 0, S goes to 1, and A goes to empty. Good enough?
What does that mean on
So
the machine?
does that mean
A goes to 1.
A goes to
Good question. Right, how do we turn this into a machine? Maybe the backwards way isn't as easy as Shai said in class when everybody was nodding and they wanted to get to lunch. And yeah, I believe you. Wait till I get there. Let's turn it into a machine. Liar. You lied to us again. Again, you're not going to go wrong identifying non-terminals as states. And in fact, you should get used to this kind of connection, because in the next level up, it's not quite as straightforward, but the gist of this idea is still there. So now what? On a 0, I go to state A. On a 1...
1, you go to B. 0, you also go to B.
Wait, no, but not from S. Oh, from here. So from 1, I go to B. And from 0, I go to B. And a 0, I go back to S. Yeah, no.
From A goes to
Oh,
A.
thanks. Okay, and now B goes to 1S. So this isn't hard so far. No problem. It's just this stuff that might be a pain in the neck, right?
A is a final state. Well,
Yeah, A is a final state, you sure?
Yeah. Well, yeah, A goes to B.
We might want to put an additional state being the final state, and then just do epsilon moves
Or
to
one
handle
to-
this
one to
A
0 moves.
A to 1 and B to 0. So if you do an epsilon move from A to the final state,
Mhm.
and then a 1 from A to the final state, and then a 0 from B to the final state, and 1 from S to the final state.
So Doug's got a plan here for how to take care of these terminal symbols, and I think it's a good plan. But before we do it, or get into the details of it, let's go through the idea of A going to epsilon. That means A's got to be a final state because you could disappear there. That seems legitimate to me. Okay, if A can disappear, then we want anything that ends up in A to be accepted. But now we have these harder ones. And the thing is, these didn't show up in our conversion the other way. In the conversion the other way, we had a more special kind of grammar, and these didn't show up. At least the way we did it, they didn't show up. But now we have A goes to 1, and what do? And Doug's got a suggestion that I think I understood. Correct me if I'm wrong, but you want to go ahead and just make a other final state over here where it goes on a single 1. Is that it?
Yeah, sure.
Good enough? And B goes there from 0, and S goes there from 1, and this is just a dead state after this,
Yeah.
right? Nothing, no other things. Is that okay?
You got multiple ones coming out of it.
Yeah, so I get a non-deterministic machine, right?
Which we already have.
But as far as what it accepts, it's doing the right thing. There's some non-determinism here too. Think of what's going on in a grammar. Grammars are by their nature non-deterministic. You don't know whether to continue generating 1b or whether to stop and have the a disappear and be replaced with a 1. That choice is indicated right here. Either we read a 1 and continue our generation of the string, or we read a 1 and we're done. Either way, as long as there's a way to accept the string, as long as there's a way to generate it, then we should be able to. So doing this backwards with Doug's idea, which is a fine idea, everything's fine except we end up generating a non-deterministic machine. This is one more motivation for the idea of non-determinism. It fits well with the natural orness of a grammar. So how do we know that this connects? Well, this direction you get a non-deterministic machine. You can always convert that back to a deterministic machine, and that completes the whole cycle. Okay? So we can really go both directions.